The aerodynamic properties of cylinders and bluff bodies in general have been a subject studied for more than 60 years. Our investigation focused around how the asymmetrical addition of a tripwire to the cylinder body affected the wake and drag of the flow around it. Much the same way that golf balls utilize dimples to prematurely transition the boundary layer from a laminar to a turbulent flow, we believed that a tripwire could have the same effect on the flow around a cylinder. This boundary layer tripping is a technique used to delay flow separation, since turbulent flow has a larger, more full velocity profile that is more resistant to flow separation and reversal in the boundary layer itself. Delayed flow separation causes the overall wake around the body to be smaller, which creates less pressure drag on the body. While the addition of a tripwire or dimples or other boundary layer tripping device creates more friction drag, overall, this contributes less to overall drag at higher Reynolds numbers as the flow velocity increases, since as Reynolds number increases with velocity, so too does the relative effect of pressure forces with respect to frictional forces. Additionally, we were attempting to examine how the tripwire affected the vortex formation and shedding through flow visualization, but time constraints in our prescribed lab time only allowed us to take picture and video of the baseline configuration's performance. The cylinder flow experiment was conducted at Cal Poly's own low-speed wind tunnel, located in Building 41. The test section for this lab was modified to hold a specialized cylinder against the walls of the test section. 24 pressure taps were mounted in the surface of the cylinder at 15-degree intervals to each other and were connected to a Scanavalve Radbase 4000 transducer bank. A LabVIEW virtual interface was used to collect this pressure data in addition to free stream velocity at the test section inlet. An additional port was connected to measure stagnation pressure in the wind tunnel was used as a reference to identify the port in the cylinder that was at the stagnation point. To trip the boundary layer, a tripwire was secured across the length of the cylinder with aluminum tape directly below the port that faced towards the flow direction, as shown by the red dot. For our experiment, we wanted to calculate cylinder drag for 3 distinct Reynolds number cases. One case of laminar flow with a Reynolds number on the order of 10 to the 4, one case of transitional flow with a Reynolds number on the order of at least 10 to the 5th, without exceeding a free stream velocity of 30 meters per second for safety reasons, and one intermediary speed with a Reynolds number halfway between the two. Thus, we chose to run the tunnel at speeds of 100, 350, and 600 RPM, and originally planned to run at least 3 trials at each speed for data collection in the cylinder's original configuration, and 3 trials at each speed with the tripwire configuration. During our testing time, ambient pressure was approximately 18.8 degrees Celsius and ambient static pressure was 100.79 heptapascals. At around 100 RPM during our test, smoke was added to the wind tunnel inlet to visualize the vortex shedding behavior of the flow around the cylinder, and it was lit from above using portable high-power lights. Other groups were able to illuminate the smoke with a laser sheet, but our testing time was in the early afternoon, so laser visualization was not feasible due to the ambient lighting from the sun. However, due to a malfunction of the LabVIEW data collection interface, our initial data for the baseline configuration was lost and could not be recovered. We thus collected data at each speed for only 2 trials each in the baseline configuration. Due to lab time constraints, we then attached a tripped wire to the cylinder and collected pressure data at these same 3 speeds for 2 trials at each speed. We then cleaned the lab and removed the tripwire from the cylinder. Here the phenomenon of vortex shedding and laminar flow can be seen at a Reynolds number of around 20,000. The shedding of these vortices is due to the formation of an adverse pressure gradient along the surface of the cylinder wall, which causes the boundary layer to separate from the surface of the cylinder. This detached flow then accelerates past the cylinder's rear surface, causing a drop in local pressure. This local pressure area then accelerates the flow from the other side of the cylinder, which forms another adverse pressure gradient and repeats the cycle on the other side of the cylinder. The frequency of this shedding is directly proportional to the Reynolds number of the flow and can cause undamped oscillation if it matches the fundamental frequency of the object in the flow. To prevent such unwanted oscillation of the cylinder, we kept the wind tunnel's free stream velocity from exceeding 30 meters per second. Another group that had performed their experiment in the evening managed to use a green laser to illuminate the smoke in the wind tunnel flow and shared their images with us so that we could better illustrate the vortex shedding phenomenon at slightly different testing conditions. Although the image resolution is not very high, the individual vortices can still be seen off of the trailing edge of the cylinder. Now on to the pressure readings we obtained from our data. All of our graphs of coefficient of pressure are compared with theoretical inviscid potential flow around a cylinder, and the differences between the two are shown to demonstrate that this is a highly viscid, highly imperfect, non-ideal scenario that we collected data for. In this first case here, you can see the static gauge pressure for our cylinder operating at 100 RPM. The mean velocity was approximately 3.1 meters per second, and the Reynolds number was on the order of 2.67 times 10 to the 4. You can see here and compare it to the trip strip case, the large region of pressure on the lower half of the cylinder and the increased drop at around 90 degrees down counterclockwise. You can compare that to our data for 600 RPM in the untripped condition. Notice the very low pressures at the rear of the cylinder due to the highly turbulent boundary layer formation. If you compare the untripped condition with the tripped condition, you see that same region of low pressure at around negative 90 degrees on the cylinder. This is due to the trip wire forming a region of low pressure further ahead of the filled and delaying boundary layer separation. You can actually compare these two cases at high and low Reynolds numbers in the tripped and untripped conditions. You can see many of the same geometries in the distribution of the coefficient of pressure over the entire cylinder. For our first set of runs, we ran the wind tunnel at 100 RPM to produce an average mean velocity of around 3.1 meters per second and a Reynolds number of 2.67 times 10 to the 4. This gave us a relatively high-speed laminar flow so that we could compare it with a higher speed transitional or turbulent boundary layer formation, and ultimately allowed us a better baseline to compare with that high velocity flow. All right, here we see our next set of runs at 350 RPM, producing a mean velocity of 11.8 meters per second and a Reynolds number of 7.8 times 10 to the 4. You can also see in our 600 RPM graph where we ran it at an average velocity of around 21.2 meters per second and a Reynolds number of 1.41 times 10 to the 5th. Here we see our coefficient of pressure graph for the tripped condition at 100 RPM, producing a mean velocity that was around 3.2 meters per second and a Reynolds number of 2.14 times 10 to the 4. You can also see here our graph at 350 RPM with an average velocity of 12.3 meters per second and a Reynolds number of 8.16 times 10 to the 4. And our run at 600 RPM at a Reynolds number of 1.42 times 10 to the 5 and a mean velocity of 21.4 meters per second. In order to calculate the drag coefficient, a panel method was utilized. This method breaks down the cylinder into 24 equally sized panels, centered about each pressure tap. The pressure data recorded can then be used to calculate the average force in the direction of the flow at each port. Skin friction can also be calculated using the ambient testing conditions and average flow velocity. The addition of these two forces can be found to be approximately equal to the total force on the cylinder in the direction of the flow. From this total force, a drag coefficient can be found for each testing condition. This drag coefficient was then plotted against Reynolds number for both the baseline and tripwire configurations. Note that the error bars plotted represent the standard deviation and not the total error of the values. To calculate friction drag, each panel was considered as a flat plate with a unique Reynolds number, and tangential velocity was calculated at each pressure tap based on the dynamic pressure. The friction drag coefficient for each panel was then calculated and used to find the total drag on the cylinder, which then was used to find the total drag coefficient. The overall drag coefficient in the baseline configuration, taking into account both friction drag and pressure drag, was around 0.57 for the three speeds, and in the trip configuration the drag coefficient was around 0.62. This means that our tripwire had the effect of increasing drag on our cylinder at all three speeds, which is likely due to the fact that although flow separation was delayed, it was still likely separated far ahead on the cylinder than we had intended in order to reduce drag. Additionally, our baseline configuration's drag coefficient was well below what would be the theoretical drag coefficient for a smooth cylinder, though this may be due to our use of the flat plate approximation to calculate friction drag instead of a more accurate and complex method like CFD. In summation, our team learned 3 valuable lessons from performing this experiment. The importance of flow visualization as both a primary data source and a qualitative means of verifying hypotheses, as evidenced by our videos which allowed us to view and interpret the phenomenon of vortex shedding. The practical applications of a working knowledge of vortex shedding, which can be utilized to design safer aerodynamic structures for either industrial or research purposes, and the importance of having a robust, flexible lab procedure when systems malfunction or break, as in the case of our first 30 minutes of data collection being lost due to a malfunction of the Z drive.